Hello and welcome to Physics 1401. Today I'm going to continue to solve some problems regarding Newton's second law and relative velocity and some collaborative problems or comprehensive problems from the book. So let's start with this one. For reference, this is number 62 if you have the book. But I'm going to explain what it is. I'm going to read it to you. A 2-kilogram toy locomotive is pulling a 1-kilogram caboose. The frictional force of the track on the caboose is 0.5 newtons backward along the track. So we have a track and we have the locomotive, and there is this car attached to it. And it's going, let's say, in this direction, and the masses are, let's call this M1, that's the caboose, which is 1 kilogram, and let M2 be the mass of the locomotive, and that's 2 kilograms. And there is a friction force on the caboose that comes from the track. Since it's moving to the right, the friction force should be to the left, and that is 0.5 newtons. 0.5 newtons. And here's the question: if the train's acceleration forward, which is to the right, is 3 meters per second square, so the acceleration is equal to 3 meters per square seconds, what is the magnitude of the force exerted by the locomotive on the caboose? All right, this force here, what is that? Okay, now here we have a system of two objects, M1 and M2, and they accelerate as one object. Okay, so both M1 and M2 have the same acceleration. What we need to do is to isolate the caboose from the locomotive and draw a free body diagram for it, and show all the forces acting on the object. Okay, so we're going to isolate this. This is isolation, right? And draw a free body diagram for that object, which is M1. Okay, let this represent M1 here. Now, what are those forces? Well, we have F, the locomotive pulling it forward, right? That is the positive X direction. So let's show it right here. A force to the right, an unknown force, which we're trying to find, F to the right. On the other hand, we have the friction force, which is in the opposite direction. That's 0.5 newtons, and it's to the left. Now, in addition to these two forces, of course, we have the weight of the caboose, Earth pulling it downward. I'm just going to call it M1 times G. That's what weight is equal to, right? M1G. And the tracks also exert an upward force. In addition to the friction, which is horizontal, there is a force, the normal force, if you will, which is along the y-axis, up. This is the normal force, Fn. N stands for normal. Remember, normal means 90 degrees. Okay, it's 90 degrees to the x-axis, or the surface in this case. So that's pretty much it. Okay, and the free body diagram is not complete until you show the acceleration also. Okay, as an arrow, but you don't attach the arrow to the object. You just put it on the side. That's your acceleration. Okay, now we have everything. This was step 1. If you want to use our methodology, the first step, always draw the free body diagram. Free body diagram. And what is step 2 then? The second step will be applying Newton's second law. Right? Step 2, apply Newton's second law. In other words, the net force acting on an object is equal to its mass times acceleration. Okay? The sigma here means sum of forces, everything here. Now this is a vector equation. I kept the arrows on top of F and A, which means that I indeed have two equations, okay? Because the x component of the left hand side should be x equal to the x component of the right hand side, and same thing for the y as well. We're not really interested in what's happening in the y direction though, because that's not what is asked. Okay, they don't ask us what the friction force is, what the normal force is. So let's not worry about that. Okay, I mean we can find it if we want it. That would be simply m1 times g, but we don't need it. But in general, this will give us two equations, one in the x direction and one in the y direction. So the x component of the net force, in other words, right? We have capital F to the right and little f friction to the left. So F plus negative F, or F minus F. So F minus F would be the x component of the net force, which will be equal to mass, which is m1, times the x component of the acceleration, which is a. After all, a does not have any y component, right? So I'm just going to write m1 times a. Now this equation is alone enough to tell me what f will be equal to, but just for completeness, let's also write down the equation in the y direction. We have fn upward, and we have m1g downward, therefore negative, equals mass times the y component of the acceleration, but acceleration doesn't have any y component, or 0, right? So it is equal to 0. That's the second step, just writing out the equations, writing the equations that come from Newton's second law. And step 3 will be simply solving these equations. In general, you will have two unknowns in a given problem, and two equations is there. So you can solve for two unknowns, but in this case, only the x equation is enough. So step 3, solve the equations. In this case, solve for what? F. Okay, so take the second equation. We have f minus f equals m1a. Now add little f to both sides. So you will have f equals m1a plus f. Okay, so m1 is 1 kilogram. Acceleration is 3 meters per second square. And the friction force is 0.5 newtons. So these will give me 3.5 newtons. All right, that's it. So that's the magnitude of the force exerted by the locomotive on the caboose. All right, that's the force. Let's do another one. How about another train problem? Let's do another train problem. Number 66. Are we recording, by the way? Let me check real quick. Okay, it is recording. An engine pulls a train of 20 freight cars, each having a mass of 5 times 10 to the 4th kilograms with a constant force. Okay, I'm not gonna draw all 20 cars. Let's see, I'm just gonna draw 3 of them. 1, 2, and then there are many here, and then maybe the last one, that one that carries the engine, right? So, okay, there are 20 of them, each having a mass of 5 times 10 to the 4th kilograms, it says. But there are 20 of them. And there's a constant force acting on these cars. The cars move from rest to a speed of 4 meters per second. From rest, the initial speed is 0, and the final speed, or at a later time, actually 20 seconds later, it is 4 meters per second. So they're moving in this direction now after how many? 20 seconds. T, or delta T, is equal to 20 seconds. It's a straight track. Neglecting friction, what is the force with which the 10th car pulls the 11th one? Aha, okay, the 10th one pulling the 11th one at the middle of the train. So why don't we do this? Let me modify the picture I just drew here. Let me add, okay, let's move it this way. Okay, so let's put dot, dot, dot. Here's another one. Okay, so this is actually 20, but let's number these. This is number 10. This is number 11. So this would be number 1. This would be number 20. Hopefully my picture makes sense here. But neglecting friction, what is the force with which the 10th car pulls the 11th one? So right here, this force is what I want to find. F. Okay? So, now here's the thing. I obviously need to isolate some cars. I need to focus on objects so that I can draw a free body diagram. But if I isolated, say, the 11th car only, even though there is no friction, I would still have to worry about the force the 12th car on the left would exert on the 11th car, right? Well, I don't want to mess with that because that's going to introduce another unknown to the equation. I don't want that. So what are the knowns? The mass of each car is known, and the kinetic information is given, from which I can calculate the acceleration. Okay, so I know the mass, I know the acceleration, therefore I can find, in principle, the force. So why don't I do this? Let me take the cars on the left, from 11th car to the 20th car, and treat that part of the train as a single unit, a system. Okay, so I'm going to isolate that part. So let's isolate it. I'm just going to put those dot dash line here and treat this as an object with a total mass of, how many do I have? I have 10. 10 times m, right? So 10 m's. That's how much mass I have there. So the free body diagram, for instance, would look like this. I have this object now, which represents those 10 cars on the left. I'm just going to write 10m here. 10m. Now the reason I do it is I know there is nothing behind the 20th. That's the last car. Okay, Okay, so if I only consider external forces on the system, I only have F, which is to the right. Okay, of course there's the weight and there's the normal force, but as you've seen, as you saw in the previous example, they did not matter when I tried to find the horizontal forces, right? I mean, I can show them here. There's of course a normal force, and there's also a weight, but the weight of the 10 cars in total. Okay, I can show them, but I'm not going to use them, all right? The only thing I need is the force in the horizontal direction. And I also have the acceleration, of course, which I need to place on my free body diagram. So if you write it out like this, actually it's really simple. F equals ma, right? Just multiply 10m by the acceleration, which we will find in a second, and you're done. That's the force the 10th car exerts on the 11th car. All right? In other words, that's the force that is exerted on the system on the left as a whole. That force accelerates that system. Okay, so how do we find the acceleration? Well, we have a steady speeding up from 0 to 4 meters per second in 20 seconds. So find the change in the speed and divide it by the time interval, and you're done. So V final minus V initial divided by delta t. I mean, you would recognize this as the definition of the average acceleration, but in this case, a constant acceleration is present because there's a constant force. Therefore, average and instantaneous are the same, and this formula is practically works out. So we have 4 minus 0 divided by 20 meters. I'm sorry, seconds. Okay, so that's my acceleration, and then I'm going to multiply it by the total mass, which is 10m, and I'll be done. Let's say mass times acceleration, and the mass here is 10m, where m is this number times a, so 10 times m, 5 times 10 to the 4th, and the acceleration is 4 over 20 meters per second square, and the answer will be in terms of newtons, right? So just finish the calculation, and that's your force. Okay, let's do another one. A helicopter. Okay, there's a helicopter problem. Number 68. A helicopter is lifting 2 crates simultaneously. One crate with a mass of 200 kilograms is attached to the helicopter by a cable. Okay, so let's try to draw the helicopter here. Okay, and the crate. Attached to the helicopter by a cable, it says. And that is 200 kilograms. M1, let's say 200 kilograms. The second crate with a mass of 100 kilograms is hanging below the first crate and attached to the first crate by a cable. So in a similar fashion here, I have the second crate, which is 100 kilograms. All right. As the helicopter accelerates upward at a rate of 1 meters per second square, so the acceleration vector is upward with a magnitude of 1 meters per second square. What is the tension in each of the two cables? The tension. Tension is the force in a cable. And we have two cables, so we're talking about two values for tension. Okay, tension in the upper cable, let's call it T1, and now we have another one, T2, in the lower cable. So what are these? Okay, now we have two unknowns, all right? This problem has two unknowns, and we'll need two equations to solve this. There's only one dimension, the y direction, that is actually useful. There's nothing really happening in the x direction or the horizontal direction. So where do we get two equations? Okay. In the previous examples, we had at least x and y directions, so we could have two equations. But how are we going to get two equations in this example? Simple. We're going to draw two free body diagrams. Actually, for each mass, we're going to draw a separate free body diagram. Okay, remember, your starting point is always the free body diagram. So all you have to do is to isolate them. If you isolate M1 here, okay, this is M1. What are the forces on M1? T1 is pulling it up. That's tension 1, the tension in the upper cable. And T2 is pulling it down. Okay, that's why I put two arrows on each cable, just to show you that fact. Depending on what object you're focusing on, the tension, the direction of tension will be away from the object. Are we done? No. M1 also has its weight. Earth is pulling it downward. So the weight, M1G, I'm just going to show it with a second arrow that points in the negative y direction. M1G. Okay, and no free body diagram is complete without the acceleration. So I'm just going to put an arrow here pointing up. That is A. This A will also be the acceleration of the second body, right? They have the same acceleration. So I'm isolating the second object now. Now, if I'm focused on M2, T1 has nothing to do with it, okay? I mean, everything T1 does to the system is going to be transferred to the second mass through the second cable. So T2 is enough. That's all I need to put there. T2. But T2 is, of course, pointing away from the object, therefore up. What do I have downward? The weight of M2, M2G. Okay, and one more thing, of course, I need to show the acceleration. And both A and both M1 and M2, they share the same acceleration, A, which is upward. Okay, so there are the two free body diagrams I need. Step 1 is finished. Step 2, writing F equals ma, Newton's second law. The net force acting on an object is equal to its mass times its acceleration. So only focus on the y direction. There's nothing really happening in the x. 0 equals 0, if you will. But if you write the second law for the first free body diagram, what do we have? We have T1 pointing up, T1, and T2 and M1G are pointing downward. Therefore, they will have the negative in front of them, minus T2 minus M1G, okay? So I just added everything, but the ones pointing up are positive, ones pointing down are negative. So that is nothing but the left-hand side of this equation, sigma F, sum of the forces. So pay attention to the notation, okay? I'm not using the arrows anymore because I'm just working in terms of components, all right? The y component of the net force doesn't need arrows, so I just drop the arrows. On the right hand side I have MA, M is M1 of course, M1 times A, which is 1 meters per second. Okay, so that's the equation I get from the first free body diagram. From the second free body diagram, what do I get? T2, which is up now. Okay, in this case, for M2, T2 is pointing upward. For M1 it was pointing downward, that's why I put it with a negative sign, but for this free body diagram on the right, T2 has a positive sign, it's pointing up. M2G pointing down, the weight is pointing down, it's also negative. M2G. That's it, we have only two forces along the y direction, and that's equal to M2 times A. Alright? So what do I do now? I just solve for T2 and T1. You can start with the second equation. So this is our third step now. Step 3. This was step 2. And the first step was the free body diagrams. Okay, so solve the second equation for T2 by adding M2G to both sides. Okay, so G plus A. M2 is 100 kilograms. G is 9.8. And A is given to be 1. Okay, so I get here 9.8 plus 1, 10.8. 10.8 times 100 is this many newtons. Okay, T2 is found. Now take that T2 and plug it into the first equation to solve for T1. T1 is T2 plus M1G plus M1A. So we have here 1080 newtons plus M1, which is 200 kilograms, times A, same A, 1 meters per second plus 9.8 meters per second square. Okay, so you finish this and you get your tension in the upper cable. Okay, so let me stop the recording and let this cat out. Alright, so this was another example, example 68. Let's check 69. Number 69. What does it say? An accelerometer, a device to measure acceleration, can be as simple as a small pendulum hanging in an airplane cockpit. An essentially similar accelerometer is found in the inner ear of vertebrates. Suppose you are flying a small plane in a straight horizontal line and your accelerometer hangs at a constant angle of 12 degrees behind the vertical, as shown in the figure. Okay, so pretty much what I just said is this. You have this pendulum attached to the ceiling of your plane or whatever is in motion. So this would be normally vertically like that, but because of the acceleration, now it is at an angle. It's your pendulum, okay? A Pendulum is a mass attached to a string, pretty much it. But this is the direction of the motion of the airplane. Direction of plane. Okay, so it is accelerating to the right, and this is what you observe. The pendulum makes 12 degrees with the horizontal. What is your acceleration? That is the question. Okay, so this accelerometer is within a plane. If the plane were not accelerating, no matter how fast it moves, you would see the pendulum straight down, okay, vertical. Now, if it is not vertical, this means you're changing your speed, all right? Changing your speed, and therefore acceleration is present. So what do? We draw a free body diagram. Remember, that's our first task. Draw a free body diagram. Free body diagram for what? For the object here. Let's call it a mass M. Now we're not given what the mass is. Doesn't matter, as you will see in a minute. It doesn't matter. Just draw your free body diagram as if you knew everything, like the mass and the tension, which will be inside the cable and all that, right? So use symbols, pretty much. This is your mass. Now let's show the forces. We have the tension in the cable. Right? The tension in this string, cable, whatever it is. And that vector T now makes an angle of 12 degrees, again, with the vertical. Okay, so I mean, whenever you have two parallel lines and a third line intersecting that line, you have same angles on sides, right? So that's 12 degrees there. All right, what else do we have? Now, we have its weight, of course, which is downward. Okay, so this vector which points downward is the weight of that object, which is simply mg. Now, some people here would be tempted to introduce a third arrow, a force, to the left. Okay, I mean, that's kind of a deceptive picture, because if it's tilted, I mean, you don't see anything really holding it there, but you say, okay, there must be something there, otherwise it would go back to the vertical position. So why is it making that angle? There must be something pushing it. So let me put a force here, like that. Okay, I mean, that you could be tempted to do that, but that would be wrong, all right? There is no such force. Some people would call it a fictitious force, all right? Fictitious because in the reference frame of the plane, it appears that way, okay? It appears something is pushing it to the left. But in reality, you don't need any force like that, okay? Remember, we isolated the object, and we're only showing the forces acting on the object. There's a physical connection of the rope. There must be a contact force there, I mean, right? I mean, you can't avoid that, and there is indeed. So we put the T. There's no question about that. And Earth definitely pulls it downward, so mg is also there. But we don't need a third force. This is enough. The two forces are enough. Make sure you include your acceleration, though. Okay? A. So we're looking at the system from a frame which doesn't really include the plane. We're looking at it from outside the plane. All we see is an object accelerating in front of our eyes to the right. And that is the object that is attached to the string. Okay? So it has to have an acceleration. We observe it. Now that you took care of the free body diagram, the rest is just like the previous examples, meaning use your F equals ma. F. Okay, we also call it the net force. Remember, the net force is defined as the vector sum of all the forces equal to mass times acceleration. That's Newton's second law. But remember, it is a vector equation, which means there are two equations hidden in it. If you think in terms of components, the x component of the left-hand side is equal to the x component of the right-hand side, and same thing for the y. The y component of the left-hand side is equal to the y component of the right-hand side. So I need to write two equations, one for x and one for y. Now, in the x direction, I have a component from the tension. If you put a box around T, okay, a rectangular box like this, you will recognize the sides of this box, this one and that one, as the y and x components of T, the tension, right? So in the x direction, of course, I need this side, which is side opposite to 12, because this side is equal to this, because we have a rectangle. So we're considering the definition of sine 12, because it is the opposite side of 12, all right? And T being the hypotenuse. So opposite side divided by hypotenuse is sine 12 by definition. Therefore, the opposite side will be equal to hypotenuse times sine 12. Okay, so when I write the equation here, I write T sine 12. Okay, so T sine 12 degrees is the x component of the net force. Happens to be the x component of the tension, since mg doesn't have any x component. So this is equal to, what do I have on the right hand side? M times A. So M, the mass, times A that we're looking for. Okay, A has only one component, that is the x component. I don't need to write AX. I could if I wanted to, but AX is A, right? There's no AY. Good. So what about the y direction now? In the y direction, now I need to focus on this side, which is side adjacent to 12. So that side divided by hypotenuse is cosine 12. Therefore, the side adjacent is equal to hypotenuse times cosine. So T cosine 12. And it's pointing up, therefore positive. But mg is pointing down, therefore negative, minus mg. Now this is nothing but the y component of the net force. Y component of F net has to be equal to the y component of MA, but A doesn't have any y component, it is 0, so I write 0 here. Okay, so those two equations are nothing but Newton's second law, written in terms of components. One vector equation gave me two equations such as these. Step 2, done. Step 3, solving the equations, doing the math. Okay? What are we looking for? We're looking for A. So we're going to solve for A. Where do I have A in my equations? In the first equation. Good. But I have too many unknowns here. I have T. I don't know what T is. I have M. I don't know what M is either. So what do? I have 3 unknowns but 2 equations. How do I solve this problem? Okay. But if you look carefully, you can get rid of or eliminate T and M. Okay. So do this. Write the second equation as t cosine 12 equal to mg. Right? Add mg to both sides. So I have t cosine 12. Good. So the first equation is t sine 12 equals ma. The second equation, t cosine 12 equals mg. What is sine over cosine? Okay, I mean this applies to many problems, and you will see this a lot, right? What is sine over cosine? That's tangent, right? Tangent 12 is by definition sine over cosine. Okay, if I multiply both the numerator and the denominator by the same number, does anything change? No. So let's multiply it by t and t here. But what is t sine 12? That is ma. And what is t cosine 12? That is mg. Okay, so m cancels, and I have a over g, and g is 9.8 meters per second square. Therefore, acceleration is, now you only consider this and that. These are equal to each other. So multiply both sides by 9.8. So this times tangent 12. This will be your acceleration. Okay, so 9.8 times what? Tangent 12. Make sure your calculator is set to degrees, not radians. And the answer is 2.08 or 2.1, let's say. 2.1 meters per second square. Okay. So that is the acceleration, the accelerometer measures. Okay, so let's do another one and then move on to maybe relative velocity. Okay, let's do 93. Two blocks, masses M1 and M2, are connected by a massless cord. If the two blocks are pulled with a constant tension on a frictionless surface by applying a force of magnitude T2 to a second cord connected to M2, what is the ratio of the tensions in the two cords, T1 over T2, in terms of the masses? So a bunch of words, but let me just draw the picture here, which will be this. You have M1, which is attached to M2 with a cord in between. And then there's a second one, a cord attached to M2. Okay? So the tensions that are involved are T1, just copying the picture here, and T2. Alright, so find T1 by T2. That's the question. Find this ratio in terms of the masses. And there's zero friction, so ignore friction. Okay? And we don't have to worry about the normal forces and the weights either, which happen in the y direction. Let's just write down the equations, or well, let me draw the free body diagram, because it's our rule. So we isolate the objects. Isolate M1. So this is M1 now. And then if you isolate this guy, that'll give you a second free body diagram. Okay, so I said we don't need the weights, but let me just show them. M2G and M1G. And of course the normal forces fn1 and fn2, they're separate, right? So they're not equal. But the real interest here is the tensions. For M1, it's a force pulling it to the right, T1. When you come to M2, there's still T1, but it's pointing to the left now. Okay, this guy here, T1 is pulling M2 to the left, but T2 is pulling it to the right. Now, what about acceleration? Now, there's not a word about acceleration here, but in general, we can include it here in the free body diagrams. So if the system is accelerating, each mass is also accelerating with A. Okay, just read the problem to see if there is any hint about acceleration. Sometimes they will say with constant speed. Okay, they will not say acceleration, but they will say constant speed, which will give you zero acceleration. Constant speed means zero acceleration. So let's read the problem again. Okay. Well, they don't say anything about speed or acceleration, but they say something. They say frictionless surface. Okay, frictionless surface, that's a clue there. The system has to accelerate. Okay, so there is nothing, for instance, consider M1. If there were acceleration, that would be pointing to the left. And if that acceleration happened to be equal to T1, then the acceleration would be zero, right? If the friction force, if the friction force, which points to the left, were equal to T1, then you would have zero acceleration. So, although they don't mention anything about acceleration or constant speed or changing speed, they say zero friction, which guarantees that the system is actually accelerating. Okay, so far so good. There are no numbers in the problem, just symbols, and we're going to use symbols. We're going to write down F equals ma only in the x direction. So what I need is the x component of the net force. That will be equal to the x component of ma, right? Which is just a. So, but I have two free body diagrams, therefore I will have two equations. So from the first free body diagram, in the x direction I have T1. That's it. T1 is the x component of the net force, which has to be equal to mass times acceleration, m1, because I'm doing it for the first free body diagram, m1 times a. That's it. From the second free body diagram, what do I have? I have T2 now pointing to the right, therefore positive. This is the positive direction, positive x, let's say. But T1 is pointing to the left. So it goes into the equation with a negative sign, minus T1. That will be equal to mass times A. What is mass? M2, not M1, but M2 times A. That's it. So that's my second equation. I want to find T1 over T2 in terms of the masses, which means I don't need to have acceleration in the answer. Means I have to get rid of the acceleration. Now you can do the same trick we did in the previous problem. You can divide the first equation by the second equation, therefore a's will cancel. Or you can solve the first equation for a, which would be T1 over M1, and plug it in the second equation. Doesn't matter how you do it, okay? So let's do it like that. Let's solve the first equation for A, which will give you T1 over M1, and plug that in the second equation. So M2 times A, which is T1 over M1. But I also have T1 on the left-hand side. Remember, there's a minus T1 on the left-hand side. So if you write it here, T2 minus T1. So why don't I move that T1 to the right-hand side? In other words, I'm going to add T1 to both sides to get T2 equals M2 over M1 times T1, which is just this, plus the T1 that I carried from the left. Okay, so I got rid of A, and I only have T's and M's. I just need to group them. On the right hand side, I have two terms, but they share T1. So why don't I factor T1 out? If I factor T1 out, I will have M2 over M1 from the first term, and from the second term I have just 1. Okay? That's how I factor them out. Because if I went backwards, I would distribute T1 over the two terms, and I would get that over above the line, right? So, in the above line. So, that's how you factor it out. And all you have to do is to divide T1 by T2. Okay, divide both sides by T2, and you will get 1 on the right-hand side, left-hand side. So, you can now divide both sides by M2 over M1 plus M1 plus 1 as well. So you will get this T1 over T2. Let me move it this way here. Okay, T1 over T2 will be equal to that 1 from the left hand side divided by this factor, M2 over M1 plus 1. There you are. Okay, you have the ratio of T1 to T2. If you wish, you can simplify this a little bit. I mean, you can leave it like this, doesn't matter. Or if you can, if you want to make it look different, you can equate the denominators on the right-hand side. So this will give you M2 plus M1 divided by M1. In other words, M1 divided by M2 plus M1. Okay, doesn't matter, but that's pretty much the ratio of the tensions, and this was 93. An odd numbered problem. We can check the answer. Chapter 3, problem 93. M1 over M1 plus M2. Okay, so let's now move on to relative velocity. Actually, you know what? There are some elevator problems here. Let's do one more problem before we move on to the relative velocity. Number 73. It says, a man lifts a 2-kilogram stone vertically with his hand at a constant upward velocity of 1.5 meters per second. Okay, so this elevator is moving up with a constant velocity, it says. So but he's holding an object in his hand. Okay, it's a 2-kilogram stone. And the elevator is moving up with a constant upward velocity of 1.5 meters per second. All right. What is the magnitude of the force of the stone on the man's hand? I think they meant the force on the stone, not of the stone. So I'm going to draw an arrow here that represents the force that the hand exerts on the object. Okay, but according to Newton's third law, we know that the force that the object exerts on the hand will be the same, only downward. Okay. So from the wording of the problem, this is how I understood it. What is the force on the stone on the man's hand? And we're giving a constant velocity. Now, what if it was not 1.5 meters per second, but 1,000 meters per second? Would it matter? Okay. Actually, no. As long as you're moving with constant velocity, you are in a frame where you wouldn't experience any fictitious forces. If you remember a couple of problems back, right? I think it was the accelerometer problem. So if there's no acceleration, the velocity doesn't matter. Okay, it's constant. Acceleration is 0. So all you have to do is to draw a free body diagram here for the object he's holding. That is mass. And what are the forces then acting on the object? Well, of course, the hand exerts a force on it, which is what we're trying to find. But there's also Earth pulling it downward. That's the weight of the object. And that is mg. So if you apply F net equals ma along the y direction, all you have is F upward and mg downward. That will be your net force. And the net force is equal to 0 because A is 0. Therefore, F is equal to mg. Okay? 2 kilograms times 9.8 meters per second square. So we have 19.6 newtons. All right. In other words, there is no net force on the object. Now, let's modify this problem slightly, and that will be number 74. Now we have acceleration, okay? The same picture. So, same problem, but A is not 0. There is acceleration, an upward acceleration of 1.5 meters per second square. Okay, same picture, but now we're accelerating. Again, the velocity at an instant has nothing to do with what we're going to do here. Okay, velocity could be anything at any instant. We don't care. We just care about the value of the acceleration. So the net force is expressed the same way because the free body diagram is the same, but now we have acceleration. So F minus mg is the net force, but now it's not equal to 0, but it's equal to m times A. Alright, so you solve for F, you get m times A plus g, and then you plug in numbers and you're done. Okay, A is 1.5 and G is 9.8. Okay, so finish this and then you get your force. Okay, so now let's do some relative velocity problems, and I'll be done after that problem, or 2 problems, I don't know how many. Let's do 79. It says a car is driving directly north on the freeway at a speed of 110 kilometers per hour. Kilometers per hour. And and that is north. This is the velocity of a car. I'm going to call it VC. How about that? VC. Now there's a truck, and the truck is leaving the freeway driving 85 kilometers per hour in a direction that is 35 degrees west of north. So VT, T stands for truck, is 85 kilometers per hour, and that is 35 degrees north of west. I'm sorry, west of north. West. Let me draw a picture then, huh? So VC is a vector which is, okay, up is north in my picture, down is south, and west is left, east is right, let's say. Like the map, right? So this is VC, and VT is this. That is 35 degrees. All right, so those are two velocities. What's the question? The question is, what is the velocity of the truck relative to the car? Now, a little bit notation here. What is the velocity of the truck, VT, with respect to the car, or relative to the car? I'm going to use a comma. Okay, velocity of the truck with respect to car. And I want both magnitude and direction, so I'm going to put an arrow here. I want to find this as a vector. Okay? So these vectors, which are given, are actually with respect to the road, right? So by VC, I really mean VC road, VCR. Okay? And here the truck, VTR. R means road. All right? So how do I find VTC then? Now maybe I need VTR here. That's given. What if I add VRC to that? What happens? Now we are given VCR, the speed of the car with respect to the road. What is this VRC, R comma C? Well, our notation actually means that would be the speed of the road with respect to the car. For passengers in the car, okay, the car is not moving, but the road is moving in the other direction, right? So if I flip the indices, it's pretty much changing the vector's direction by 180 degrees, okay? That's what it really is. So in other words, VRC is the negative of VCR. Okay, so that I know. VCR is actually pointing up. Okay, so we have this vector equation that looks like this now. VT comma R minus V RC. All right, so all we have to do is to write this vector equation in terms of the components. Okay, you can call it x and y, or you can call it east-west and north-south. So in the east-west direction, for instance, that'll be like the x component, right? So what is the component? What does it give you? Now, here's your equation. VTC. Now, VTC in the east-west direction. East-west. Okay, so that will be the east-west component of this on the right-hand side. Okay, so what are the components, east-west components? Now, VTR is actually 35 degrees west of north, so its east-west component will be negative. It'll be equal to negative hypotenuse times sine of 35. Why sine? Just box it like we did before. If you draw a box around it, we basically want to find this here. That's the east-west component, which is also this. And that is side opposite to 35. Therefore, I need the sine, okay? So, and it's pointing to the left, therefore it will be negative. So it'll be negative hypotenuse, which is VT, that is 85, times sine 35. 85 kilometers per hour times sine 35 degrees. Okay, that's for the first term. Now from the second term, which is VRC, I don't get anything. See, I mean VCR is up and VRC is downward, but same thing. I mean, they don't have, it doesn't have a x component or east-west component. So put a 0 there. There you have it, 85 sine 35. So 85 sine 35 is just 48. So I have here negative 48 kilometers per hour. Now what about the north-south direction? Okay, now when you do the north-south direction, north is positive, up in my convention, so I need 85 cosine 35. 85 kilometers per hour times cosine 35. That's from the first term. Now from the second term, what do I have? Now there's a minus sign here. VRC, which is negative VCR, and that is, where is it here? 110. 110 kilometers per hour. Okay, so 85 cosine 35 minus 110, that is negative 40.37, well, let's say 40.4 kilometers per hour. Okay, so we found the components. We can just use the square root formula to find the magnitude. And then you can use the arctangent to find the direction. Okay, so 48 squared plus 40.4 squared. Take the square root of that, you get 62.7 kilometers per hour. .63 kilometers per hour. Okay, if you round it, 62.7 becomes 63 kilometers per hour at 40 degrees south of west. 40 degrees, how do you find that? You can use the arctangent. So south of west, this angle, okay, theta I call it. How do you find theta? The arctangent of the northwest component, that is 40.4, and east-west component, that was 48. So 40.4 divided by 48. Take the arctangent of that, 40.08 degrees. Okay, that's how we find the direction. All right, so this was 79. Let's do one more and then I'm gonna stop. Okay, let's do one more relative velocity problem. Actually, you know what? How about the problem with friction? With friction. Well, we did friction problems in the previous chapter, but we never did a friction problem that has to do with Newton's second law, right? So let's do that. Let's do 103. It's a long one. Let me try to read it. The coefficient of static friction between a block and horizontal floor is 0.35. So we have a horizontal floor and a block and friction between the two. The coefficient of static friction is 0.35. And the kinetic coefficient of friction is 0.22. Mu kinetic is 0.22. And the mass of the block is 4.6 kilograms. And it is initially at rest. V initial or V0, V initial, VI, doesn't matter. VI is 0. At rest. So, A. What is the minimum horizontal applied force required to make the block start to slide? Minimum horizontal force. Okay, so that you apply this force and the object will start to slide. Now, if you remember from the theory of friction, right? If this force is less than a certain value, the object will not move, all right? Which means there's an opposing force to it, and that is a static friction force. Fs. And what you do, you increase the force you exert on it. In return, the static friction force also increases. Okay? As long as the object is at rest, the two forces, F and Fs, will be equal to each other in magnitude, only opposite in direction, but they're going to be equal. So Fs is not a fixed number. It depends on F that you're pushing it with. Okay? So if you draw the picture, let this x-axis represent the force you push it with, and let this one represent the friction force. It'll be a line. On that line, the two are equal to each other, okay? So on this line, F will be equal to F until it starts moving. When it starts moving, the friction force will be a constant value, which is less than the maximum friction force available. So this is the maximum value of the friction force. So that's the minimum horizontal force we need to move it, okay, so that it starts moving. So the minimum horizontal force needed turns out to be equal to the maximum friction force which is available from this system. And that is a fixed number, of course, which is nothing but μs, that is given to us, times the normal force between the object and the surface, the normal force. Okay? So that's the plan. We're going to find the normal force and multiply it by μs to get the maximum friction force, which will be equal to the minimum horizontal force required to move this object. How do we find the normal force? Now we can go to the second law, Newton's second law. F net as a vector is equal to mass times acceleration. Just draw the free body diagram for this object, m, with mass m. Show the forces on it. Big F, that's you pushing it to the right. Little f, friction force. F normal, up. And its weight, mg, downward. Okay? It's not moving yet, so acceleration is 0. Therefore, F minus F is 0, and Fn minus mg is also 0. Okay? So that's how you find Fn. Just solve this equation, which will give you Fn is equal to mg. Therefore, Fs max will be equal to μs times Fn, which is mg. Okay, so 0.35. Does mu have a unit? No, these are dimensionless numbers, no unit, just 0.35. M is 4.6 kilograms. And G, 9.8. So multiply these, 0.35 times 4.6 times 9.8. That gives you 15.778. Okay, you can round it to 16 or just leave 15.8 newtons. All right, that's the minimum horizontal force. Part A, done. What about part B? Let's read part B. Once the block is sliding, means we are in the kinetic phase now. Kinetic phase. If you keep pushing on it with the same minimum starting force as in part A, which is 15.8, does the block move with constant velocity or does it accelerate? Okay, good question. Now, you may think, okay, I already have my equations, and the first equation said here, F minus F equals to 0, so the net force is 0, therefore there is no acceleration. That would be wrong, because that equation was written with the static phase in mind. Okay, the object was not moving That's why I put zeros on the right hand sides. But now the object is moving. All right? The object is moving and we're in the kinetic phase. Now, can the object move with a constant zero acceleration, constant velocity? Yeah, but it's not the case. Why is it not the case? Because if you look at this picture here, the figure carefully, this horizontal line here represents the kinetic friction force. And that is a little bit less than the maximum friction force, maximum static friction force, okay? So recall that the kinetic friction force, which is a constant, no matter how hard you push it, it's a constant, it's less than the maximum value of the static friction, which means it will not be equal to 15.8, okay? So let's rewrite the equation now. F minus F, but this F is Fk, not the static force. This Fk will be less than 15.8, therefore there will be acceleration. So I have to write m times a here. Okay, so the answer to part B is yes, the object will accelerate, and this is how you find A. Okay, that's how you find A. Can you find A? Yeah, we can. Just divide both sides by m, and you will get F minus Fk divided by m. But what is Fk? Now, by definition, Fk is equal to mu k times the normal force. So you're dividing this by m. Now, the normal force doesn't change just because the object starts moving. The normal force is still mg, okay? So A is equal to F minus mg times, or let's say mu k mg. Let's not forget mu k mg divided by m. Okay, now this F, of course, can be anything. It depends on you. In part B, it says you keep pushing on it with the same minimum starting. If that's the case, you can just plug in 15.8 right there, and mu k is 0.22, mg, you know what mg is, and divide by m, you get your acceleration, okay? So that's how you find acceleration. There's another part here that says if it moves with constant velocity, what is its velocity? Now, if it moves with constant velocity, this means that you're not pushing it with 15.8 newtons. Actually, you're pushing it with something less than that. Okay? Can you find that force? Yeah, I mean, just take this acceleration formula and equate it to 0, and the force required to move it with constant velocity will be equal to mu k mg. Okay? But can you find the velocity from it? Now, it's not, it's ambiguous here because you have to reduce the force you apply, okay? And you don't know how much time has elapsed and how you reduce that force. Those information are missing. So there can't be a definitive answer about the velocity. You can still find the acceleration, yes, assuming that you're pushing it with 15.8 newtons. That would be actually speeding up, not constant speed, okay? So you can't find the velocity, but you can only find acceleration. Okay, let's check our answers for this, and then I'm going to stop there. So chapter 3, problem number 103. 16 newtons. Okay, 15.8, 16 newtons. The block will accelerate, yes. And 1.3 meters per second square. it says. Let's check it. So let's plug in 15.8 here and minus 0.22. 0.22 mg 4.6 9.8 divided by 4.6, so 15.8 minus 0.22 times 4.6 times 9.8, divide this by 4.6, 1.27 goes like that, so 1.3, okay, 1.3 meters per second square. Okay, so you can find the acceleration but not the velocity. If it was something like what will be the velocity after 10 seconds, then yeah, you could find it. Okay, but unless you have that information, you can't find the velocity which is changing. Okay, so I'm gonna stop here and I'm gonna make another video for the coming chapter, which is about motion with constant acceleration, such as free fall under gravity. Okay, so till next time, goodbye.